In the last episode, we covered two out of the three kinds of intermolecular forces, dipole-dipole interaction and the London forces. Dipole-dipole interactions is a special kind of intermolecular forces between polar molecules. London dispersion exists among all kinds of molecules, however, because it is usually weaker than dipole-dipole interaction, it is only significant for nonpolar molecules. Now we're going to go over the third kind of intermolecular forces that is called hydrogen bonds. Hydrogen bond is an unusually strong dipole-dipole interaction. It exists only between a special kind of molecules. In these molecules, there's a hydrogen atom connected to a unique kind of atoms. That unique kind of atoms must be 1, high in electron negativity, 2, small in size, and 3, has a lone pair of electrons. To satisfy these three conditions, there are only 3 atoms, fluorine, oxygen, and nitrogen. So when hydrogen is connected in the molecule, when hydrogen is connected to fluorine, oxygen, or nitrogen, there will be a special kind of attractions between two molecules. We call that hydrogen bonds. So what is it? How there is such kinds of attraction? Let's take a look at it. Because it is an intermolecular force, so I'm going to draw two molecules. And because it is unique for hydrogen bonded to the atom fluorine, oxygen, nitrogen, when we draw the molecules, I'm going to focus on the bond between hydrogen and the atom. So what it is in this part of the molecule, I don't care, but I need to have a unique atom X bonded to hydrogen. This represents one molecule. I'm going to draw another one here. This represents another molecule. Again, what is here for the molecule? I don't care. I only focus on the bond between hydrogen and the unique atom. All right, this atom X is high in electron negativity. What does that mean? That means the shared electrons between X and hydrogen is not really shared. It is very close to X other than hydrogen. It is small in size. That tells you the electrons is very close to the nucleus of the X. Both of these factors resulted in one fact. These shared electrons are not really shared. They're very close to the X other than hydrogen. As a result, this hydrogen carries significant amount of positive charge. Again, it is not a full charge. A full charge will make it into an ion. This is not an ion, but it's very close to one full charge. Now this hydrogen has only one electron. Now it is almost lost to the X, which means the outside orbital of hydrogen is almost empty. Now, X has a lone pair, remember that. This lone pair will interact with the empty orbital, almost empty orbital from hydrogen. This attraction is called hydrogen bond. Remember, hydrogen bond is a kind of intermolecular force. It is not really a chemical bond. The reason we call it hydrogen bond is because in some special occasions, it can get so strong that it behaves very similarly to a chemical bond. But in general, it is still way weaker than a chemical bond. All right, let's see what this one's trying to say. The highly electronegative element to which hydrogen is bonded attracts the bound electrons to such a degree that hydrogen is left with a significant plus charge. Yes, we talked about this. The small size of the bare hydrogen nucleus allows you to approach closely and be strongly attracted to the lone pair. All right, we covered all of this. This picture shows us the hydrogen bonding situation between water molecules. So let's focus our eyes on the center water molecule. I'm going to draw it on the side here. Water molecule, there are two hydrogens on it. There are two lone pairs on oxygen. As you can see, first, one lone pair can interact with a hydrogen from another molecule. That is a hydrogen bond. Another lone pair can do the same thing to interact with another hydrogen in another molecule. That's another hydrogen bond. At the same time, the hydrogen can interact with the lone pair from oxygen from another water molecule. That's another hydrogen bond. Same thing here, that's another hydrogen bond. So a water molecule can form up to 4 hydrogen bonds with other water molecules. 2 by offering lone pairs, 2 by offering hydrogen atoms. Keep in mind, a water molecule can form up to 4 hydrogen bonds. However, it doesn't have to form 4. It may form 1, 2, 3, or 4, or maybe even 0. But it has that capacity of 4. How many hydrogen bonds can a methane molecule form with other methane molecules? Methane molecule, this is a methane molecule. I'm drawing it here right now. That's the Lewis structure of methane molecule. How many hydrogen bonds can it form with other molecule of itself? 0. 0. Why? Because these hydrogens are connected to carbon. Carbon is not a fluorine, not oxygen, not nitrogen. So these hydrogens cannot form hydrogen bonds. Okay, so methane molecules cannot form hydrogen bonds between them. What about a methanol molecule? A methanol molecule, again, I'm going to draw the Lewis structure here. A methanol molecule. These 3 hydrogens here are useless. They are not capable of forming hydrogen bonds because they are on carbon. Now this hydrogen is on oxygen, so it can form a hydrogen bond with a lone pair from oxygen from another molecule. At the same time, this lone pair can interact with another molecule, hydrogen on oxygen. That's another hydrogen bond. This one can do the same thing. So it can form up to 1, 2, 3 hydrogen bonds, 2 by offering lone pairs, 1 by offering hydrogen. Now let's look at the relationship between the intermolecular force and the boiling points of a substance again. We did this on the last episode right after we finished London dispersion. At that time, our conclusion was for related compounds, the bigger the molecule, the higher the boiling point, because when molecules get bigger, the London dispersion gets stronger. So the vapor pressure of liquids that have significant hydrogen bonding are much lower than those of similar liquids with little or no hydrogen bonding. I hope that makes sense. Hydrogen bonding is the strongest intermolecular force. Stronger intermolecular force, lower vapor pressure, higher boiling point. All right. So the low vapor pressures for compounds with stronger intermolecular forces with hydrogen bonds usually is lower. When the vapor pressure is lower, boiling point will be higher. Compounds with strong hydrogen bonding have relatively higher boiling points. All right, here is a series of compounds, which is this, H2X. X is an element from column number 6A elements. So oxygen, which is H2O, sulfur, H2S, selenium, H2Se, tellurium, H2Te. Well, if you look at this, the boiling point is getting higher and higher. Makes sense because the molecule is getting bigger and bigger. And that was our conclusion from the last episode. Now, if this trend is kept, water should have a boiling point somewhere around negative 80 degrees Celsius-ish. However, not only water's boiling point didn't follow this trend, but it is unusually high. It is 100 degrees Celsius. Why is that? Because between water molecules, there is a special kind of intermolecular force, hydrogen bonds, which is the strongest intermolecular force, way stronger than the other two kinds. As a result, the water's boiling point is unusually high. Concept check: which are stronger, intramolecular bonds or intermolecular forces? Well, we did this at the beginning of the last episode. Intermolecular forces are weaker compared with intramolecular bonds. Those are chemical bonds. If you heat a liquid to boil it, the intermolecular forces are overcome, but the chemical bonds are not broken. Which has the stronger intermolecular forces? Nitrogen? Water. All right. Of course, water. We know water has hydrogen bonds. Nitrogen is a nonpolar molecule. It only has London forces, one of the weakest intermolecular forces. All right. So water has a stronger intermolecular forces. It has all three kinds: hydrogen bonds, dipole-dipole, and London forces. Below are the Lewis structures of two molecules with the same formula. Okay, both of these have 2 carbons, 6 hydrogens, and 1 oxygen in them. All right. Which of the two will have a higher boiling point? Well, anytime a boiling point question is asked, it is a question about intermolecular forces. So which one will have a higher boiling point? It is asking you which one will have a stronger intermolecular forces. Well, in the second molecule, clearly you see a hydrogen bonded to oxygen. So you know between these molecules, if you have more of these molecules between them, they will have hydrogen bonds, which is the strongest intermolecular forces. Therefore, higher boiling point. Which gas would behave more ideally at the same conditions of pressure and temperature? More ideally, what does that mean? That means it will behave more like an ideal gas. An ideal gas is a gas that has zero attractions between molecules. Molecules are independent from each other. So whichever has a weaker intermolecular forces, whichever has a weaker intermolecular force, that one will behave more ideally. So let's draw the Lewis structures of carbon monoxide and nitrogen. Polar molecule, nonpolar molecule. So nitrogen is a nonpolar molecule. It has a London force. Carbon monoxide is a polar molecule. It has dipole-dipole and a London force, and dipole-dipole is way stronger. As a result, the intermolecular force between nitrogen molecules is weaker, so nitrogen will behave more ideally. That's all for today.